All right, an example of a joule would be one, converting between calories, joules, kilocalories, kilojoules. And so you just have your conversion, and then we just have our conversion factors there. Two, predicting how much energy is required. And so here, if you burn 2 moles of ethane, this is ethane, you generate 2,855 kilojoules worth of energy. And so the example is we use that as a conversion factor. We did an example of this in class where we used it as a stoichiometric conversion factor with any of these. Same thing with ammonia. If you want to decompose ammonia into nitrogen chloride, it's going to cost you 92 kilojoules. So that's if we want to decompose 2 moles. What if we want to decompose 4 moles of ammonia? How much energy would it cost? 2 moles is 92 kilojoules. 4 moles would be double that, so 184 kilojoules. This is pretty much how we use it. What if we want to decompose 1.365 moles of ammonia? Then we want to set up the ratio because it's a little harder to figure out. So the ratio is for every 2 moles of ammonia, it requires 92 kilojoules. So those are stoichiometric conversion factors. And so we did this example in class, the calcium carbonate decomposition. And then we looked at a bunch of homework problems with this kilojoules in there as well. And so you do stoichiometry and you do interconversions. That's it. Were there any other questions?
No.
How about anybody else? All right, today we're going to continue discussion. Where did we leave off last time? The light bulb, right? You talked about the sun and the tungsten light bulb, then the hydrogen light bulb. Hydrogen light bulb was a bit weird. What was the problem with the hydrogen light bulb? It didn't show all the colors, and what that means is that the electron cannot possess any energy it wants. Did I talk about the wave particle duality of the electron? No. So basically, for the free electron, we see a continuous spectrum. The free electron, we would see that like in the sun. You know, there are free electrons moving about in the sun. Those can move at any speed they want. They can have any energy they want. And they can't get too high in energy, so we see infrared and lower energy and visible. So the sun and the tungsten light bulb, the incandescent light bulb. You know, those are examples of the continuous spectrum where we see all the colors of the rainbow here. But if we look at the hydrogen lamp, they're discontinuous spectrum. You know, there are only 4 colors observed, 4 colors. And that means everything in between was forbidden. And so electron could not possess certain energies. And so the first person, I mean, you know, this observation, this would be like the hydrogen lamp. Also tungsten, if we have a piece of tungsten metal, that behaves differently than like atom. If we're looking at tungsten atoms, then tungsten atoms don't emit a continuous spectrum. They don't give white light. They would give some other kind of discrete spectrum. These two spectra look totally different, you know. The hydrogen lamp and the tungsten atom lamp. And so when we say here, this is a free electron, when we have an electron confined to an atom, they behave differently. An electron's confined to an atom, it's not allowed to have any energy it wants. And so the theories that resulted from this, one is the Bohr theory. The Bohr theory was proven to be incorrect. What the Bohr theory involved was the idea of orbits. You know, the electron could only have certain orbits that were allowed. You can't be a little farther or a little closer. It has to be this exact energy. So if the energy were a little less, it orbited a little closer to the nucleus. If the energy were a little bit more, it orbited a little farther. But none of these energies in this region were allowed. In other words, no orbits were allowed in between those allowed ones there. And so this is the whole idea of the orbits. In other words, when we think about the energy, this would be like a continuous continuum of energies allowed, because this person can step at any gravitational potential energy height they want. But this quantization, that is this discrete levels, there are only 1, 2, 3, 4, 4 allowed steps, that's it. And you can't have anything in between. It just was forbidden. And so why would the electron do that? That means if we're on the first floor here, you have to jump up to the second floor. There's no 1.5 floor. Or there's no 1 1/4, or there's no 1.1 floor. It's first floor, second floor, third floor, and that's it. And so Bohr had this idea of allowed orbits. These are called orbits, allowed orbits. Everything else forbidden. And it was postulated, what's the proof? Well, the proof is this is what's observed. We don't see all the colors of the rainbow, so therefore that's the way it must be. But the theory should give a more fundamental picture of what's happening, and yet this is kind of just taken without proof. Taken without proof it's called a postulate. This would be a postulate of quantum mechanics. One of the postulates is these are allowed, everything else is forbidden. But theory should do more than give a fundamental description. Theory should also do what? Theories need to give a more fundamental description. Well, the fundamental description of why not all energies with electron are allowed. The fundamental description is this: they aren't allowed. That's it. They just aren't allowed. Therefore, these are the only ones that are allowed, like this. And so there are a whole bunch of orbits. The orbits, we have the n equals 1 orbit, then the n equals 2 orbit. There's actually a bunch of these allowed, all the way out to n equals infinity. When we hit n equals infinity, the electron is essentially ionized, that is, removed from the atom. And so if an electron goes from the n equals 1 to the n equals infinity, it's gone, pretty much. Interestingly enough, the energy is not infinite energy. The n equals 1 energy is here. But what happens is the orbitals, or not orbitals, orbits diverge. So this is, an infinite distance out. The energies converge. And so the n equals infinity energy is up here, So there's a big jump from n equals 1 to n equals 2, and then the jumps get smaller as we get to higher and higher numbers. And so I have to fit an infinite number of lines between the first one and this one here in a finite amount of space. So the orbital energies get crunched up, the orbits themselves spread out, but you know, the picture is fundamentally wrong, because the theory should give a description, and it should, well, the description is this. The description is, we look at this part of the spectrum. Let me blow it up a little bit. The description is that these colors result from the electrons moving from one floor to another. And so this is n equals 2 here, n equals 1. And so if an electron were here and the n equals 2 and it drops down here, then what happens is a UV photon, a UV light is emitted here. However, if we go 3, 4, 5, 6, 7, so this would be n equals 3, n equals 4, n equals 5, 6, n equals 7 here. Then the allowed energies correspond to what we call electron transition. And so if we had an electron, let's say the electron jumped from here up to here, n equals 3. And so when the electron gets to the third floor, it could drop to the second floor, or it could drop to the first floor. If it drops to the second floor, it emits a red photon of light. Red. If we go from the fourth floor to the second floor, then we get green. If we go from the fifth to the second, we get blue. And then the sixth to the second, we get violet. So violet, let me write like that. Blue would be a little longer wavelength. Green would be longer wavelength. And red would be the longest wavelength here. Like that. If we go from the seventh floor down to the second floor, then what we see is UV. If we do the fourth floor to the third floor, then we get IR, infrared. And so that's kind of the fundamental description. It's this electron. Electron can jump to higher energy orbits, and then when it falls back down, it emits the light that we observe in the UV, the infrared, the visible parts of the electromagnetic spectrum. So that's the fundamental description. But the theory should do that plus what else? Theory should be able to predict. And this is how it was proven to be wrong. The Bohr theory couldn't predict the spectrum or any other elements. Could not predict spectrum for other elements. And so it was abandoned. This whole idea of orbits, is wrong. And what replaced it is this. Okay, this is the kind of the picture of what's happening. Energy can be absorbed. So from going from n equals 1 to n equals 2 requires UV. Then as it drops down, it emits UV. So 984 kilojoules going up, 984 kilojoules per mole going down. Energy is conserved. Destroyed. So this idea of orbits on the left is wrong. Instead, what replaced it is the quantum mechanical model. The quantum mechanical model, there are two things that were added. Not everything was wrong about Bohr. One thing that wasn't wrong is that there were forbidden energies and there were allowed energies. And so the quantization of energy remained. It's just, how we visualize the electron changed dramatically. And so after Bohr came two important developments, quantum So, two important developments. One was the wave-particle duality. The electron is both a wave and a particle. So electron has wave properties like light, but it also has particle properties like a physical object. So, wave particle properties. And the second is something called the Heisenberg uncertainty principle. Let's say you're going to make a musical instrument. So you have a musical instrument, and you can change the sound. Let's say a string instrument. You could change the sound, right, by shortening or lengthening the string, right? Or making it tighter, making it looser. So let's just keep it at one tightness here, and then what we're going to see is that. We're going to see quantization of that string. And so this is called a standing wave. When we consider, I don't want to be standing waves. When we look at standing waves, something has to happen in order for it to be allowed. And what has to happen is it starts and ends at the same place. So let's take a look at something like this. So this is what we call a half wavelength here. So a half wavelength is allowed. Let's say the string is attached here and it's attached here. But could you have a quarter wavelength? That is, could you fit a quarter wavelength? You start here and then attach this part there. No, you can't have it because the string is attached in two fixed positions. So a half wavelength is allowed, and then this shows a full wavelength or two half wavelengths. So we could fit two half wavelengths in there. Or we could fit three half wavelengths. Or we could fit four half wavelengths. And so the energy of the string is quantized here. We could have, this would be n equals 1, this would be n equals 2, n being the number of half wavelengths, n equals 3, n equals 4. Could we have n equals 1.1, or 1.5, or 1 3/4? Are those allowed or forbidden? Those would be forbidden. This is what happens. This would be like a confined electron. A confined electron is confined to the space. Versus this, another way of thinking about this is, let's say you're a whale. You're a whale confined to a small pool. Are you allowed to move any speed you want? No. You go to SeaWorld, those whales can't move at full speed. In fact, they gotta move at some speed where they can turn around, go back the other way, maybe. And so that's going to restrict the energies that whale can have. And so this is the same thing. A free electron in the sun it has all the room it wants. It's like out in the open ocean. It can move any speed it wants. Therefore, a continuum of energies is allowed. But when you take that free electron, which is, it has the entire sun to move around, you take that and you confine it to a tiny atom. That's like taking a giant whale and putting it in a tiny pool. All of a sudden, it's going to be very restricted in terms of what energies we want. And so this whole idea of standing waves, or this whole idea of wave property, wave particle duality of an electron, things naturally come out quantized. Now this is in one dimension. Let's take a look at what this looks like in 2 dimensions. Okay, so what they did here was they put, this is just a metal plate. And what they did was they spread out some powder on the surface of the metal plate. And then you can see what frequencies are allowed for this metal plate. We can see what frequencies are allowed by just listening to this and then watching what happens to the powder plate.
Walk away purposely not to hear that yourself.
The highest frequency there? Yeah. They should have turned the volume down, but you have to hear it, otherwise.
Yeah.
So these are forbidden energies for the plate. Sorry. You turned down the volume. All right, this is allowed right here. Do you see that? That's allowed. And then this is forbidden. Forbidden. And this would be allowed, the next higher energy that's allowed. And so you can see the patterns are different for a two-dimensional plate like this. Now if we have three-dimensional, then they look different, these wave functions. And so let's take a look at this here. This is what it looks like in 3 dimensions. And so this would be allowed. This is a very simple structure. This is spherical. This is a little bit more complex. This is a little higher in energy. These are like figure 8 type dumbbell shaped orbitals. And then if we go higher in energy, then we get a clover leaf shaped like this. And as we go higher and higher in energy, it changes the way it looks. So this is allowed, allowed, allowed. Everything else is forbidden. And so we have quantization of the electron energies there. All right, what do we call these then? We don't call them orbits, like the allowed orbits. We call them orbitals. Orbitals. So these would be orbitals here. And so, two things you want to know about the orbitals. The orbitals are, one, well, actually, I'll talk about this thing in just a second, but let's let me take a step back and say where the orbitals come from. And so these two concepts were added to the quantization of energy, and then we came up with quantum theory, quantum mechanics. In quantum theory, the orbitals describe the allowed states for the electron. They come from the Schrödinger equation. The Schrödinger equation is just the physics of this. If you incorporate the weight properties of the electron along with other standard physics concepts, we can come up with the Schrödinger equation. From the Schrödinger equation, then we get the solutions. For each atom, the solution to the Schrödinger equation tells us the allowed energy. So the solution equals an orbital. And it turns out that there are infinite number of orbitals allowed. There are also an infinite number of forbidden ones as well. And here, what we do is we pinpoint the energy. So it tells us the energy. However, the position is going to be poorly defined. Position is not well defined. Well defined. These last 2 points here deal with the Heisenberg uncertainty principle. This is a result of the Heisenberg uncertainty principle. Heisenberg just said you can know one or the other. You can know one with precision, but the other would be not so precise. Or you can know both, but not so precisely. For us, we want to know the energy. And so here, if we know the energy, that is, we pinpoint the energy, then its position is not well defined. We can use like a bird nest analogy for this. Let's say there are other ways to think of it. Let's say we have just a bird with normal energy. A bird with normal energy has a nest here. And let's say in one instant of time the bird is here. And so we know where the bird is in this instant of time, and it has this amount of energy. Let's say 30 seconds later, can you pinpoint the position of the bird 30 seconds later? No, that's like the electron. 30 seconds later, where exactly is that electron? I don't know. It might be here. And so the best thing to do is to track it, over time. If you track it over time,
if it has a normal amount of energy, it's going to be not far from the nest. But sometimes it might get a little farther. Most of the time it's close. And so once in a while it might be kind of far out there. This. And so this is the type of picture we generate for the electron. Orbital. And so what this shape shows is this. The shape like this says, this is an artificial boundary. You know, it's not even a wall. You know, it's just some made-up boundary to indicate that there's a 95% probability that the electron will be inside this boundary, and a 5% probability that the electron will be out. And so that's all we can do for the electron, just like the bird. The bird will just say there's a 95% probability of finding the bird within this boundary here, and the 5% probability of finding it outside that boundary. So based on the Heisenberg uncertainty principle, what we end up with is electron probability distributions. That we call the electron cloud. So there are different ways to represent it. One way is to represent like this sphere here, or the shell. So the 95% probability of finding the electron within here. And what gives rise to these shapes are the wave properties of the electron. Another way of visualizing this is like this, where we draw a cloud like here. You know, we can't pinpoint the electron in some orbit. Instead, we can just draw this. The greater the density of dots, the higher the probability. So as the density of dots decreases, so does the probability. And then we draw this artificial boundary around this, saying that's 95% of the dots are in here, 5% of the dots are outside here. Okay, let's say if it has a normal amount of energy. What if the bird has higher energy? If the bird has higher energy, then the distribution is going to be a little bit different. So if the bird has a higher energy, let's say the next higher energy, since there's going to be a jump, you know, it can't have any energy it wants. The bird has to have this energy or the next allowed energy. The next allowed energy is it's like this, so it's got more energy. If it's got more energy, it can be farther from the nest. It can also be close to the nest. And so that probability distribution spread out more. And so in other words, if we would draw the 95% boundary here, it's going to be like this big. But if we're at the next higher energy, it's going to be like this big. So it's going to look like this. And so we can see that here. This is what we call a 1s orbital. If we jump to the next higher energy orbital, this is a 2s orbital, it's going to be a lot bigger distribution. It's going to be a lot bigger because it's got more energy, so it can be further from the nest bird. All right, so the orbitals tell us the energy of the electron, and it tells us the position in terms of probability. The orbital tells us the energy and position. The energy, again, we know with precision, but position isn't, and so it's just a probability in terms of probability, since it's not pinpointed. So that's quite a bit different. And so this is a comparison here. The Bohr model versus the quantum model. Quantum model, you're dealing with orbitals, probabilities, energies. All right. So if there are an infinite number of answers to the Schrodinger equation, let's go to the hydrogen atom. The hydrogen atom, there are infinite number of answers, or infinite number of orbitals. if there are an infinite number of orbitals, then is it impossible to figure out all the orbitals? Turns out no. It's not. The lowest energy orbital is what we call n equals 1. And it's going to be a 1s orbital. A 1s orbital has a three number code. It's a 100 code. And the 100 stands for N, L, and M. This is this little sphere here. The next higher energy orbital is an n equals 2, which will be a 200 or 2s orbital. 1s orbital. The highest energy orbital is going to be n equals infinity. And so we go 100, 200. Do you know what comes next? 300, and then up here will be infinite 00, but it's not infinitely far away in terms of energy. But it turns out that the orbitals are a little bit more complex here. And so let's see how we can generate these. And the way we can generate it is these orbitals follow a simple mathematical pattern. So, for example, here, these numbers, N, L, M, have certain mathematical restrictions in order to solve the Schrodinger equation. And so when n equals 1, we only have one orbital allowed, but when n equals 2, we have what are called two subshells, or two sublevels, the 2s and something called the 2p. And the 2p sublevel is further divided into three orbitals. Here. We have the 2, 1, negative 1, the 2, 1, 0, and the 2, 1, 1. And those 2p orbitals look like this. And so the s orbitals are spherical. The p orbitals are these shaped here, and there are three of them, etc. And so what turns out to happen is there are a lot more levels than what Bohr predicted. And so the spectra are much more complex. The spectrum for an individual atom are much more complex than what Bohr had, with all these additional levels. So that's the H atom. And so the H atom is still the same thing: the second floor, first floor, third floor, second floor, etc. It turns out that when n equals 3, we have the 300. Then we have the 3, 1, negative 1, the 3, 1, 0, the 3, 1, 1. These are called the 3p, and there are three allowed orbitals there. But when n equals 3, we have the 3s, the 3p sublevel, and then we have one more, which is called the 3d. And that has 5 orbitals, 3d. The 3d consists of these: 3, 2, negative 2, 3, 2, negative 1, 3, 2, 0, 3, 2, 1, and 3, 2, 2. And so the pattern for the orbitals these have mathematical restrictions. That's what makes them allowed. And if they don't adhere to these mathematical restrictions, then they're forbidden. So what are the mathematical restrictions here? The first one is n. N is called the principal quantum number. And it's often termed the energy level. We have the first energy level, or the first floor, the second, the third, all the way up to the infinite. And so there are an infinite number of allowed energy levels. However, there are also an infinite number of forbidden ones, because something like 1.1 is forbidden. If you plug in an n equals 1.1 back into the Schrodinger equation, it comes out false. That's like this, we see mathematical restrictions. There's a mathematical restriction: 2x is equal to 6. Can x be any number? no, there's only one allowed answer for this, and that would be x is equal to 3. But for, for this, the equation's a bit more complex. So, if we plug in n equals 1, it works. If we plug in n equals 1.1, it comes out false. We have, n really tells us the energy, how high up. The greater the n, the greater the energy. So energy increases. L is called the azimuthal quantum number. L tells us the shape primarily, and secondarily it tells us the energy. But the energy is the secondary. And so what are the allowed L values? All are allowed from 0. And so here we can have 0. For the energy levels, we can't have 0 energy level. But for L, we can have 0. But we can have more than that. We can have L equals 0, L equals 1, 2, 3, 4, ... all the way up to a max of n minus 1. It's the biggest L we can have. We give these letter designations. So L equals 0 is S. An S shape is spherical, like the top one there. And then an L equals 1 is P. A P-shaped orbital is the second row, dumbbell. And L equals 2 gives us the D-shaped orbital. D-shaped orbital is the bottom row of orbitals. These 5 orbitals have the same exact energy. They just differ in orientation, slightly in shape. S, P, D, then 3 is F, 4 is G, then it goes alphabetical after that. S, P, D, F, G. Finally, M. M is what we call the magnetic quantum number. From the magnetic quantum number, we can determine the number of orbitals and orientation based on a code. The number of orbitals is equal to the number of allowed values. M's. And so what are allowed? What's allowed are all values from minus L to minus L plus 1, ... through 0, ... through L plus 1, plus L plus 1, plus L plus 2. I mean, not plus L plus 2. What am I doing? Plus L minus 1. Plus L minus 1 to plus L. And so, in other words, we're going from all values from minus L to plus L. And so let's take a look at how we can build up the allowed orbitals for a typical atom. The allowed orbitals for a typical atom start off with the lowest energy orbital, which is, what's the smallest n we could have? N equals 1. This is the smallest n. So this is going to be the lowest energy. Okay, so when n equals 1, what are my allowed L values? Well, I'm allowed all L values to max of n minus 1. And so what is the max? N minus 1. N is equal to 1, so 1 minus 1 is 0. So I'm only allowed this, 0. And so I could call that the 1s here. N equals 1 and L equals 0. It's 1s orbital. Or in number designation, it would be a 1, 0. Now what's my m value? my M values will be all values from -0 to +0. So there's only one value from -0 to +0, and that's 0. So this is called a 1, 0, 0 orbital. A 1, 0, 0 orbital, aka the 1s orbital. What does it look like? It looks like that sphere at the top. And that's when n equals 1. Okay, the next allowed n value is n equals 2. So if we go to n equals 2, there's going to be a jump up in energy. It's going to be a significant jump up in energy from n equals 1 to n equals 2. When n equals 2, what are my allowed L values? I have 0 and 1, because 2 minus 1 is 1, so the max. And so what I'm going to do is I'm going to divide this. I'm going to call this L equals 0. When L equals 0, I only have one M value that's allowed, and that's M is equal to 0. And so 2, 0 is allowed. 2, 0. Okay, when L is equal to 0, then my M value can be -0 to +0. So only one value, and that's that. So this is my 2s orbital. And so 2s orbital is allowed. But I'm allowed one more L value. The one more L value is L equals 1. When L equals 1, what are my M values that are allowed? Well, I go from -1 to +1, going through 0. And so I'll have -1, 0, +1. Now, when L equals 0, going to L equals 1, L equals 1 is a little higher in energy. So L equals 0 to L equals 1, a little higher. L equals 1 is called a p orbital, so these are my two p orbitals here. And so I'd have like a px, py, and pz. They only differ in terms of orientation. The energy is the same. In number code designation, it looks like this: 2, 1, 2, 1, 2, 1. 2, 1 is a p orbital, 2p orbital. That's N and L. This is N, L, M. So if L is equal to 1, then N varies from -1, 0 to +1. So these are my three 2p orbitals. I have the 2, 1, -1, 2, 1, 0, and 2, 1, 1. Okay, and how about this? Can I have a 1p orbital? Is that allowed or forbidden? A 1p orbital. In other words, a 1p orbital would be a 1, 1. Is 1, 1 allowed or forbidden? 1, 1. Allowed? Forbidden? Why is it forbidden? Yeah. And so there's no such thing as a 1p orbital. A 1p orbital doesn't exist because it violates the maximum L. In order to have a 1p orbital, n would have to be 1, and p gives us an L of 1. So n1, L1 can't exist. Okay, so once we have here L equals 1, we can't go any higher in L. We can't have L equals 2. Can I have an L equals 2 when n equals 2? No. So that's forbidden. And so the next thing I can go to is the n equals 3. When n equals 3, what are my allowed L values? Well, all of them. When n equals 3, I'm going to have a max of 3 minus 1, which is 2. So I'm allowed 0, the s. So I should have 3s. Which is 300. I'm allowed L of 1, which is 3p. 3p's would be slightly higher in energy. 3p's. This would be 3, 1, minus 1, 3, 1, 0, 3, 1, 1. And I'm allowed an L equals 2. for L equals 2, be a little higher in energy here. So I'm going to make it a little lot higher. My L equals 2. L equals 2 is called 3D. So if I have 3D, what are my allowed M values? Yeah. And so this is L equals 2. And therefore my M values are going to be -2 to +2. So it's going to have -2, -1, 0, 1, 2. And so how many is that? That's 5 allowed M values. So that's 5 orbitals. So these are represented by 5 lines here. With the magnetic quantum number, this is shape primarily. That's shape. The magnetic quantum number is orientation, number of orbitals and orientation. So we got these 5 orbitals with different orientation. Well, these are the 5 orbitals here, different orientations. What are they individually? They're the 3, 1, 3, 2, -2, 3, 2, -1, 3, 2, 0, 3, 2, 1, 3, 2, 2. My 3D. And then what comes next? N equals 4. I can't go to 3F because that would exceed the max. And so I have to go to N equals 4. A strange thing happens with N equals 4. When I go to N equals 4, the first orbital is the 4 L0. And so it's a 4-0 orbital, which is a 4s. The strange thing that happens is the energy here. The energy of the 4s orbital is lower than that of the 3d. So this is 4-0-0. And so the strange thing is the energy goes 4s and then 3d and then here we go to 4p. Where we have 4, 1, -1, 4, 1, 0, 4, 1, 1. And then we go to 4d. And then we go to 4f. But we're going to stop here. You should be able to draw this. This is called an energy level diagram. Up to the 4p orbital. You should be able to derive it. Now, this ordering gets all mixed up here, but one way to figure out the ordering is it follows a pattern as well. The way to figure out the ordering is to write it out like this: 1s, 2s, 2p. These are called sublevels here, or subshells. Here. 3s, 3p, 3d. 4s, 4p, 4d, 4f. And so we can figure out the ordering by drawing diagonal lines like this. So it goes 1s first, then 2s, then 2p, 3s, and then 3p, 4s, and then 3d, 4p. What would come after 4p? You know what comes after 4p? 5s. Exactly. 5s would come after. So the next one will be here. So there's some patterns here. Let's take a look at some of these patterns. Got my book, but we'll take a look at it after the break. We'll take a break right now, and then